All right, so let's get started. So this is the final lecture. And so what I want to talk about today is this. So we talked about a type of self-similar, I mean, it was an extremely abbreviated discussion, but I gave some indication of a type of self-similar solution for the Einstein vacuum equations, which corresponds to the scale invariant solutions. Now I want to talk about a type of self-similarity that corresponds to the, so now we want to do, so self-similarity. Again, we're interested in the Einstein vacuum equations, and we want one that corresponds to, which corresponds to to the K self-similar solutions. K self-similar. Okay. Now, there are different ways to introduce this. I mean, maybe I'll start with trying to understand geometrically where, like, what's an assumption that we want to break. So first point, so note for the class, for the type of solution we discussed already. We discussed um they all have they all have the following. All have the following geometric property. Namely, so you have the self-similar field. We have this K, right? Which is the self-similar field, all right? Which this thing that does this. Okay, and then what's special about this is that so you have this I mean in our coordinates it's v equals 0, but this thing has a geometric, it's not just like you can think of it more geometrically. This is the pass cone. So call this we can also call this C, say is the which is just the past cone of the singularity, right? And what happens is that G sort of the norm of K for all the ones that we discussed is equal to 0 on C exactly. Right? It's exactly null. That you just compute, right? That's just from because the shift vanishes and um yeah, it's just I mean, right, it's just because K these coordinates is just K is equal to U du plus V dV. So on V equals 0, this goes away, and d by du is a null vector. And so its norm is 0. All right. But there's no, in principle, there's no reason. You could also, but why not have something, sort of like this, where, you could have your singularity, you have your oh now I don't know if I can draw this. Some so here's your cone, it's the past cone. And so like this situation sort of corresponds to, everything is null. So like the orbits of the self-similar field just go sort of straight up and down. But they could also like twist in some way. I mean, why not? Oh God, I don't know, like something like that, right? I don't know if you kind of see what I mean. So what I mean, like why couldn't there's not like you could have something which satisfies that the Lie derivative, that's a dilation field in this sense, and you still have a scaling origin similarity, and then but then when you go along it, it does this. I mean, somehow the solutions we considered don't allow for this for whatever reason. I mean, well, which we'll get to in a second, but they don't seem to allow for that. So if you could do that, so why not have something like this? So i.e., so in this situation, so this K is still pointing along this null hypersurface, but which is sort of reasonable. I mean, if you sort of insofar as like dilation symmetries, like, it's a conformal transformation, and conformal transformation should sort of keep, you know, if a conformal transformation fixes a point, then it has to also fix the past cone of that point, right? Because it's conformal, right? So okay, the singular point is not really in the space-time, but anyway, it's sort of reasonable to think that, well, we don't want to give up the fact that the self-similar field keeps the past cone of this invariant, but why should it, why can't it have so much more complicated geometry? All right, so in this case, so for example, sort of K might be space-like on some of C bar. All right, and then if that happened, what you can sort of think, if you could find something like this, you can think that this would sort of correspond to Christodoulou's K self-similar again, in the following sense. So if you think that so when K equals 0 for Christodoulou, then, it's just that you like you rescale space-time, you rescale the space-time and get the same thing back. Right? It's like the simplest thing. You just zoom in, looks the same, right? Well, other than like you zoom in and you do the obvious adjustment of the scale, and it looks the same. All right. So then the K not equal to 0, what's a way that you can think of it? You can think that you rescale, and then it doesn't quite look the same yet because you have to shift the scalar field by a certain amount. You rescale and shift scalar field, right, by adding some suitable constant. Of course, the B depends on how much you rescaled, and then it's the same. All right. Okay. So this operation of adding a constant to the scalar field, this is like a trivial symmetry of the system, right? I mean, whenever you have just a solution of the wave equation, you can always add a constant as anything. It's almost one of the most like simple manifestations of sort of a gauge freedom. I mean, it has no, of course, you have to work with a specific scalar field to solve the PDE, but there's no, in the Einstein massless scalar field system, I mean, there's just like no physical, none of the things in the energy momentum tensor depend on phi actually. So like this concept really has no meaning. But somehow, nevertheless, you consider this sort of rescaling, which in order to see that it doesn't do anything, you have to do this gauge freedom. And somehow this coupling gives you something more complicated. Now I claim that you can think of this process as like something like this, because what's the analog? So what's the analog? We're here. So the analog of this map, phi goes to phi plus b, is instead of a scalar field, you can think that, you know, this thing is foliated by spheres. But you have, so instead you have your G slashes. All right. And what it says is that so if your K sort of twists around like this, but nevertheless is giving you a conformal symmetry, it's sort of saying that like, well, another way to say it is so this K then would have to be equal to, well, if you pick some, if you have like well, I'll write it like this. So let's suppose, so you might think this thing will be some part, say a null part. I'm going to write in different coordinates in a second, so maybe I shouldn't. Well, yeah, let's just think, you could think of it, I'll put tilde just for, these are not going to be the coordinates that we study them in. But you could imagine that you have this d by du, which is sort of like the actual null thing, and then the self-similar thing is d by du, but if it's still on the cone, it'll have to be added to something which is space-like. So then what it's sort of saying is that, you can rescale by u, and of course you won't quite see the same thing yet because you have to sort of like, as you go down, you're going to twist. So you have to undo it, but that undoing is just a diffeomorphism. So this corresponds to this is applying, pulling back by some, by some flow of B to, okay, being very rough. Right. So it's like if, if your self-similar field does this as you go down, it's like saying, all right, I flowed by one. I didn't see the same thing yet, but all I have to do is undo the twist on the one sphere. And that's very roughly like an analogy with this. All right. So, okay. Anyway, that's a very like, okay, this is all a bunch of kind of nonsense I'm saying. All right, let's think about this more concretely. That's sort of part one. All right, so more concretely, let's go back and let's think about where, um, how can we find something where this is not true to get this picture? Well, so the issue was the Ricciarduri equation. So the issue was in Ricciarduri. Right, the ingoing Ricciarduri equation, which eventually, which led us to the sort of trivial things that we had to have, even if we tried to pick the shift vector to be non-trivial, it had to satisfy, that this was zero, right? This is on v equals zero. So there was this ingoing constraint equation, which greatly constrained the geometry of the ingoing cone, right? All right. So how can we break that? Well, it's not so clear at first. So the point is to think about sort of where this equation sort of came from. I wanted to just, yeah, where's the, sorry, I thought I had this. I had scrolled to the, I tried to set it all up and with all the equations on it. Yeah, okay. So I just want to write down, yeah, Ricciarduri and think about the different terms here. So we have this, so here's Ricciarduri's equation. Um, all right, so this was the source of where all that rigidity came from, right? Because well, I converted this, trace chi bar, this gave me 2 over u, say plus div b, right? There was divergence of b, and then this thing had this trace-free symmetric gradient of b that was squared. And then here's a crucial thing. So before um we had that omega bar had to equal 0 on v equals 0. Because why? Because by self-similarity, just by the scaling, omega is equal to some function of v over u, right? And so at v equals, well, and then times theta can depend on the theta variable. But then when you restrict, you go to v equals 0, you get you just get something that depends on this. And well, I mean, sorry, you didn't get that this was 0, but it just dependent. I always forget this. It's just dependent on basically just dependent on log on LB on this, because omega bar is equal to the E3 vector applied to the laps. And the point is that the main thing I need to say is that, like, you don't sort of this thing can't have any U dependence somehow. It just doesn't work because it has to be this by scaling, and then if whatever. Okay, but now here is the sort of key idea. But what if you allow this, for example, I'll just say to be something like v over minus u, and then we put minus some kappa. All right, so what if we did that? Okay, well, you might say, I mean, that looks like it's pretty singular. All right, but just for a second. So if you did this and otherwise kept everything else the same, all right, so of course now the metric doesn't even extend to v equals 0, but it will have the benefit, but you can check that omega times this will still be okay, because this thing is, well, up to some constant. So let's not worry about the constants. I think it's, well, I'll just say some constant, and then it's going to be times du. So this thing now doesn't depend on theta in this one example I'm doing. And it's du times the log of omega. Right. This when I multiply it by this, because omega bar is the covariant derivative of E3, and E3 always has that. Remember, E3 always has this normalization, right? This thing out there. So when I multiply by omega, I get rid of that. And then the b, there's no angular dependence, so the b doesn't do anything, so I get this. And so what you see here is that you sort of, this looks singular as v goes to 0, but this quantity is still defined, right? Because the way log works, because the log will separate the v and the u, and the du will annihilate the 1 over the v, right? Because you get minus kappa, log of v minus log of minus u, and d by du of the log of v is 0. And so this, is something which will be proportional, say, to kappa over minus u, roughly. All right, with some other constants, but forget about that. All right, which means that if you allowed such a lapse, then up here, when you computed this equation on v equals 0, there would be an extra term here. You would get this extra term. Okay. But I mean, this all looks really silly, but so what, right? I mean, this thing looks horrible. I mean, this is the whole, yeah, I mean, why would you do that? Well, except that now let's remember what in our discussion of Christodoulou solutions, that when we did the K self-similar solutions, there was this issue of regularity at the pass cone of the singularity in the naive coordinates, and we had to consider a rescaled V coordinate. Okay. And a similar thing works here. Of course, well, this isn't how Christodoulou phrased things originally. But anyway, you can understand that what's going on there is that you need a rescaled coordinate. So let's look at, so remember the metric in general looks like this. So this is the metric in our normal way that we would write it. All right. And okay. And now we suppose that the lapse is like this. So these coordinates certainly cannot possibly make sense at v equals 0 because this thing is blowing up, right? But what I can do is I can define v hat, or v hat to be, let me just get, yeah, to be v minus 1 minus 2 kappa like this. Again, there was a similar thing that we did for Christodoulou. And what happens is you're going to get d, you can just compute. Right, so this thing in the v hat u theta coordinates will become, I mean, you're going to pick up, well, okay, this 1 minus 2 kappa, who cares about that? But what more interesting, you're going to pick up, well, I mean, I can write it like this, omega times v to the kappa squared. All right, and then all the other stuff's in. Okay, and now let's say for this particular type of lapse, you see, if I multiply this by v to the kappa, now it's a perfectly fine function at v equals 0. Right, so again, there's a very similar thing happened with the Christodoulou example we did. So what we did is we said, all right, we started with these coordinates where we had, remember in these coordinates, our self-similar field was k equals u du plus v dv. All right, but now you say, all right, that's fine. But what if we assume that these coordinates actually were not valid if v equals 0? And therefore, if they're not valid, then we could consider things like this. And we say, well, actually, the coordinates that are actually work to get to v equals 0, you really should do this kind of switch here. And let's also, to make our life simple, let's restrict to kappa. Assume that kappa's small, so it's not like too big of a deal. All right, so it's like almost the same, but there's some little switch. And then you do that change of variables, and then now this thing looks okay. Of course, the price that you paid, just like in the self-similar one, with Christodoulou's ones, is that this vector field, this k, will look different, right? It gets perturbed in the v hat variables, just like in the well, just like with Christodoulou. And again, you can just I'll let you do that computation. You get, I mean, you're going to get, it'll look, almost will look like u du v hat, d by d v hat, but it's going to get multiplied by some 1 minus 2 kappa or something. All right, so you get the slight deviation. So it's like, so then you sort of have this game. So now, yeah, you have this game. So you can work in these coordinates where you have the usual self-similar vector field and the usual formulas apply. And that's convenient, but they're not valid at v equals 0. And then if you want to go to v equals 0, you have to do this sort of funny change of coordinates, which of course changes what the self-similar field looks like in those coordinates, which means that like you don't have the usual algebraic relations of self-similarity. Like it's not going to be the case that things are functions of v hat over u. All right, but anyway, that's fine. I mean, we're used to that kind of stuff. For example, that's the kind of thing that happens on black holes. There's a nice coordinate. There's the sort of coordinate system that's most convenient for computing is also one that's not valid at the event horizon. And that's like, it's a little annoying at first, but it's not really a problem. You just, you compute in the one coordinate system often, and then just keep in mind whenever you want to do something on the horizon, you have to translate into the correct coordinate system. So nothing worried about that. Okay, so we can consider this. All right, so the whole point of this is, so now I sort of, in this setting, I can still look at what Ricciarduri equation becomes on v equals 0, which is the same as v hat equals 0. right? And otherwise, so I changed this thing for the laps. Otherwise, the G slash and the shift vector, again, those I don't assume that they were singular. Those are fine. I mean, you can see when I do this change of variables to the v hat, nothing here, because there's no dv here, nothing here changes, right? So leave those the same. Right? Okay, then you just have to work out now with this slightly more general sort of ansatz what happens. And well, you got one extra term corresponding to that. Well, not just one, but you get yeah, so I have it here. All right, so what you get is this more general version. So now you get, so a lot of this will look the same for before. So this is on, I mean, now you can think it's v hat equals 0, right? All right, so these are all the same terms that we saw. This was this thing that before it ended up implying that basically we could only take trivial data. All right, and then here you get, this is the crucial new thing you get. You get 4 kappa over u squared. You get this term. All right, and then you get all this other crap. Well, actually, yeah, no, okay. So in fact, for this is a more general version I can write down. I mean, I'm trying to keep things simple here. Again, you could throw on some angular function here. You could do much more complicated things, but let's keep with this sort of simplest manifestation of the principle I want to show. All right, so you end up with this equation. So this is the new term. And because of that new term ends up completely breaking that rigidity that we saw before. So what was the problem before? So what was the issue before? So remember, I just gave you a brief heuristic explanation for what the problem was last time. And the easiest way to see that is to just consider that you try to solve this equation with, you try to find some solution to this equation where b is size epsilon. So before, you said, okay, so if b is sort of size epsilon, then, all right, let me just take the leading order term. So I have div b. These things are just going to be like epsilon times div b. So roughly speaking, it's almost like I have div b is equal to, and then, all right, this part has the curl in it. So I mean, that's not controlled by div b, so I should sort of write that. So you sort of had, something like this, um, plus epsilon, you know, times div b. You had some equate roughly something like this. It's not quite true because there's an angular derivative here, but let's pretend the angular derivative of div b is sort of controlled by div b. So schematically, you had something like this. And well, then you said, all right, so if b was epsilon to begin with, remember this was epsilon squared. So then div b has to be epsilon squared. But on the other hand, I can integrate this. That goes out. And then I get that this is like epsilon cubed. And then you iterate that whole thing and it just seems like nonsense. But now you do that same process, you do that same thing, and you have this is crucial. Again, so we're setting here u equals, say, -1. So say u equals -1. Remember, the u is just different spheres. If it's true at one u, it's true on all the u's. And so you get this now. And this changes everything. So now, as long as I allow myself to sort of pick kappa, that same kind of heuristic argument that it's not going to work won't happen. Because now what it says, okay, maybe I should try, maybe I want to find a solution to this, some b solving this, but I also allow myself to change the value of kappa. Well, okay, again, just for time, I won't run. It's not that hard to make rigorous what I'm about to say, but let me just state it very informally. So roughly speaking, this is an equation for the divergence. So you might think, okay, so roughly speaking, I should be able to like sort of specify the curl and then, at least something almost like the curl of b and then solve for the divergence from this equation. All right, and before that didn't seem to work, but now what it is, okay, so you imagine an iteration process. So at the first stage of the iteration, you just you pick some like seed, some guess for b, but it's not trivial. So you just say, so you can solve this by some iteration. You just make this equal to some epsilon times, some fixed. You just fix some vector field that you start with, all right? You just plug that in, and then on and at each stage, what you do is you just plug this in, and then you pick kappa so that this thing integrates to zero. Then you can solve, you can update the divergence part of B from this equation and call that, and then, so modify the div part of that, keep the curl part, call that B1. And then you iterate, plug that in again, start iterating. Every time you move this, and the point is, because you can nudge this a little bit, you can always maintain, you can make sure this thing is in the is orthogonal to the co-kernel of divergence. So you can solve, right? Um, and so you can now you can find a lot of solutions. So the upshot is you can find there are many solutions to this with, and this is crucial, with a non-trivial B. Right? Okay, and I claim that this, so this is of course just solving the one constraint equation. But if you could now sort of complete this to, you know, now sort of keep solving, find some self-similar solution where again, it's self-similar in the sense that you have to switch these coordinates to get something regular at v equals zero. But if you could do that, I claim that it's exactly like this picture I talked about at the on this first board. And why is that? That's just because, well, think about what does b not being zero mean? So all right, so we still have that. So k equals u du plus v dv. Now you can also write it, that's in the u du coordinates. Now you can write it in the v dv coordinates and you get, all right, all right, I think you get this. Check that. All right, you get something like that. But whatever it is, it's still the case that, k, restrict it sort of to v equals zero, is u du. Okay, so the self-similar field in these coordinates. So this is why I made a point of saying that, you see, it's not, it's sort of the opposite of kind of the picture I drew. So in the picture I drew, I kind of pretended that I kind of acted like the straight lines in my picture were the null lines and my k was twisting. But somehow the coordinates that we're going to study this in, it's the opposite. I mean, everything is up, straight versus twisted is all just, it's a picture, right? It has no meaning. So, but some sense like, so these coordinates are sort of picked so that k looks straight and the null thing will look twisted, but it's of course the same. All right, and then the point is that now you look at the null vector. Of course, maybe, so let's look at, so E3 is null. Of course, E3 in principle has this division by the laps, where I wrote E3 somewhere. Okay, that's singular, so let's multiply get that out. But then you'll get something which is null still. If you multiply a null vector by a function, it's still null. It's null and certainly tangent to the cone. So that is, could be taken as a null generator. This is equal to d by du plus b. And this is not zero. Right? So that's telling you that there's this deviation between like so so if you declared the flow of these to be straight lines, then k will be twisting. So if you can go through that whole procedure that I sort of briefly sketched in the last two lectures, if you can run through that procedure starting with this, richer set of like starting data, then, you could be in business. And all right, so I have 12 minutes. So, the short version is that it works. And let me briefly indicate some of the things that you have to do to see that. So maybe it's worth just for 2 minutes to pause. Are there any questions? Make sense? Okay. Yeah, maybe it's also worth saying that, well, once you understand this construction, I mean, you see, this is in reality just one type of a much more general, there's a natural kind of most general type of this sort of self-similarity that you can do once I mean, this is the first example to understand, because this one is very simple in that you pick a particular type of lapse, which is singular, and the coordinate change which cures it is also a coordinate change which keeps you in the double null foliation. That's convenient. It's sort of, or at least conceptually. But sort of eventually you realize, there's more general classes of these kind of things that you have to do. And in those more general class, the regular sort of coordinate change will take you out of double null. And that just introduces some extra um, ultimately surmountable issues, but this is sort of easier to think about first. And this one really, it's all sort of the singularity is kind of spherically symmetric, and it's sort of just easier to think about. But you can get much more general, and if you're curious later, you can look at this paper I wrote called "Twisted Self-Similarity for the Einstein Vacuum Equations," which discusses a bit. Okay, so what are the new ingredients that then go into understanding this? Well, again, we can follow this recipe that we had from before. That is, first thing you want to do is look at these formal jet computations and see if you have freedom. You can try to apply the same philosophy. And then, assuming that works, start doing all those estimates. And again, you could proceed the same way. All right, so let's talk about these sort of formal jet computations. All right, there are lots of things that are unclear here. So one thing you might remember is also from the Christodoulou ones that they have limited regularity ultimately. So those ones were only C1, like the metric was the derivative had some Holder continuity, but it was not C2. So you might expect a similar thing will happen here. All right, which means you have to be a little careful. So if you remember, we had this stationary point of view that I said where you use self-similarity, you have a transferred equation, you had some equation like this on v equals 0, and I said you can use self-similarity. You rewrite this as some lower order thing plus v times d by dv. And then if the v times d by dv was 0, when v was 0, you got some stationary equation. Now you can still try to do that. That still can be a useful point of view, but you have to be careful because possibly the thing is going to ultimately have limited regularity. So maybe that v times dv is not 0 really. Like, right? If the thing has a logarithmic singularity, then v dv of it's not 0. Anyway, so with those caveats, you nevertheless can think that way. Yeah, let me say, so if you have an equation like this, so if you happen to know that v dv of f goes to 0 as v goes to 0, all right, then you can sort of derive in the same way we did before. So before what we said was, okay, we said if the thing is self-similar, then this has to have some particular scaling, and we eventually it was an algebraic equation. So remember, we ended up with something, it was like d minus c over, this equals whatever, something like that. And then it was, if this thing was equal to c, then, okay, if this is there, you have a problem. If it's not there, it's freedom. If it's not equal, then you just get this algebraic relation. So now what's funny is that because, well, first of all, you probably want to you want to take out this novel, you take out the lapse here because, right, principle, this thing is singular everywhere. So you multiply everything through by that. All right, and in reality, the term here, this thing was coming from a term trace chi bar, and trace chi bar is the Lie derivative with respect to E3. So when I multiply by omega, in reality, you get this, but then this is the Lie derivative with respect to omega times E3, which is actually the natural thing to do. So, okay, so you multiply this. I'm just saying that if I multiply here, this is what will give me some C over U. Okay, in reality, there's also some div B floating around. Maybe that's small, whatever. But what's more disturbing is that in this nabla 3, there's this B. Right? And so now, instead of getting something algebraic, you end up with equations which are going to roughly be of the form, you're going to get things like Lie B, the Lie derivative with respect to B, plus, whatever, let's just say some low order. So you get equations like this, right? And then, all right, and then, so you have to develop the one thing you do when you study these, you have to develop some understanding of these. One way to do these is that, okay, so let's say if this whatever W thing is here is like positive, one thing you have is there's certain a priori estimates, for example, you can prove for this. So just assume you had a solution. You can certainly multiply this by f, integrate over the sphere, integrate by parts, and you can prove something. So if you multiply by f, you'll get, and then you integrate by parts, you're going to get something like, you'll get div b f squared. You can get things like this, right? And then, okay, if this is small, remember this whole thing, we're assuming working under some smallness assumption to even solve that equation. We need some, because it's some nonlinear thing. So this is, say, small. So you can try to solve these. Of course, you might worry about, well, I mean, that's if I have a nice solution. Then I could try to commute and do it, but All right, and then, well, one way to just, there are various ways you can try to justify it. One, a nice one is just to do some elliptic regularization. So you can basically, if this estimate works, it will sort of also work with a, you can add in like a delta times a Laplacian or something. And then this is now an elliptic equation. And for each delta, and you can check that, whatever you solve it, and then take some limit at delta goes to zero. In reality, this process, if B is sufficiently small, you can do a lot of derivatives, but you sort of in principle could always come to some issue after you take like a million derivatives. As you take more, because every time you commute this with a derivative, the lower order term sort of changes, right? You hit this with a derivative, and this commutator is still proportional. It's proportional to something. Sort of a changes the lower order term, right? Um, okay, for any finite number of derivatives, you can assume that B is so small that it doesn't matter, but he sort of doesn't naturally give you smooth things. But okay, we don't really care. Maybe it's C5 million, good enough. Okay, there's that. Or um, oh no, I had more than 12 minutes before. I thought I had 12 minutes because I ended at 3:50. Yeah, so I have tons of time. I have 14 minutes. That's crazy. All right, so now, but now let me tell you. So that's all fine, and that works for some of the ones. But now let's go to the first one where things really change a lot. Or it's interesting. Anyone, I don't know, is anyone, I know this is so vague that it's even a miracle if you're following me at all. But I don't know if you have some guess where something really interesting happens. So there was one equation that, worked a certain way, but if you slightly wiggled it, I mean, what was the free quantity, right? It was chi hat, remember? So chi hat's equation, like when you compute it, the stationary equation for chi hat becomes 0 = 0, right? But now I'm sort of doing this weird perturbation. I mean, so of course, when I do this thing, I add some Lie B. It's not going to add very much, but if my equation that I'm perturbing was 0 = 0, adding epsilon to 0 = 0 could be very dramatic, right? Depending on what epsilon is. Okay, so let me remind you quickly. All right, so this is before we had this equation for chi hat, right? And what happened, and then this became a self-similar freedom. But now it looks, but now it's like really unclear what's going to happen. Because first of all, one of the results of doing this, so remember before, lots of things were just zero. Because we sort of started with, B being zero and things, and then that has a result. So for example, we saw that torsion had to be zero on V = 0. That was something I mean, mostly I asserted to you, but I vaguely showed how torsion ended up being zero. But now, sort of because B is non-trivial, nothing is going to automatically vanish anymore. So now it's certainly not the case that the junk here is not zero anymore. It's something. All right, so now it's also not the case anymore that that everything gets perturbed. This thing is not going to be exactly 1 over U anymore. And there's going to be a B here. So everything is sort of, so now, okay, so this thing is kind of the same. Of course, it doesn't make sense to consider the equation written this way is maybe not quite the right way to write it, because chi hat is probably singular, because this is the Lie derivative with respect to d by dv, and we know that v hat is the right coordinate. So we have to adjust. Okay, that's not too hard to adjust. You just multiply by v to the 2k or whatever just to cure it. That's okay. So, okay, you probably want to multiply by this. Um, uh, that's fine. So basically, yeah, so now, okay, yeah, I'll say, well, you want to multiply through by v to the 2k just to make everything regular, because chi hat's not really the right quantity. All right, this 0 is now going to give you something. It's going to be, say, small. Maybe there's something small, epsilon, but it's probably something there. The 1 over u is now going to be like it's going to be like 1 plus epsilon over u. Okay. Well, in fact, it's sort of even worse in that, in fact, sort of what you get for the stationary equation is something that looks like this. All right, so this, I also had the formula ready to go. Okay, so this is a long computation, but what you get is the following. All right, so let's go over here. All right, so let f of AB is, like, is kind of chi hat restricted to this, but multiplied by, the correct power of V to be regular. All right. So we expect that because instead of chi hat, you should really look at chi hat in this V hat coordinates. But again, we sort of like to work with the old quantities because those have nice formulas, and we just have to remember that they're not regular. So you always have to adjust. Okay. So anyway, let me not. So you do the adjustment, and let's just call the thing that you get FAB. Then the equation you get looks like the following. So you end up getting Li of FAB, and you get this. Right, and you get minus 2 kappa. All right, where HAB is sort of already known, and is like size epsilon. Right. So epsilon, remember, is sort of the size of our vector field B. Another thing I forgot to note up here, well, I can note it now. So if you think about how kappa is picked in this process, so kappa is picked to sort of cancel to make the right-hand side integrate to 0. So kappa is naturally going to be quadratic in the size of B, right? So note that kappa is like epsilon squared. Anyway, so this is the equation you get. So this looks like a pretty weird equation because you have a right-hand side, which is size epsilon. Then you have some sort of weird thing, some weird operator depending on B, whatever B is. B is size epsilon. Then there is a lower order term here, which, is a constant. And so, that's kind of nice for multiplying by F and getting something. But that constant is actually epsilon squared. All of this junk is size epsilon, and the right-hand side is size epsilon. So even if we forget about B, which we can't because it's pretty big, this equation sort of kind of looks like F equals, it kind of looks like this. So even if you forget about B, because kappa is epsilon squared and the right-hand side is epsilon. So what this sort of tells you is that F restricted to V equals 0 is in principle enormous. All right. And well, this is what happens. All right. Okay, principle. All right, but that's sort of best case scenario. But you have a more serious issue that there's all this junk. So what turns out is that you can do a lot of work. And if you call all of this stuff, right, again, I'm trying to be cognizant of the time right now. Let's call all of this, call all of that the script L operator. It turns out you can do a computation that the script L is actually an anti-symmetric operator with respect to the G slash volume form. In other words, so you can, so yeah, well, I'll just say, so this is anti-symmetric with respect to G slash, which means that I actually can get the estimate that is suggested by this. That is to say, I can multiply, well, in L2, I can multiply this by F, contract with F, integrate everything over the sphere with respect to the G slash volume form. And because this is anti-symmetric, it goes out. In the same way, when you have like dx of F, if you multiply by F, it's a total derivative and integrates out. Same thing happens here because it's anti-symmetric, right? So that's nice. So you do get this at least in L2. Then what's a very complicated story is that, well, as we've seen in these nonlinear problems, it's very important that you have higher derivatives. So you have to also control higher derivatives. But when you commute this equation with derivatives, if I just commute with some random operator, an anti-symmetric operator, I mean, you know, that just could destroy everything. So one, but it turns out, and this is something that takes a lot of work, is that you can go through this whole construction, and if you sort of start the seed data with some nice, clever choice of B, the thing that it starts with P0. You can track everything, you compute everything in the leading order. You'll get some control of B in terms of that first thing you pick. Not everything, because the divergence solves the equation, but you can still try to compute with that as a leading order, blah, 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 blah. And for certain special B, you can cook up a commutation scheme which works. All right. And you can construct solutions which are, again, C500, not necessarily smooth, but if you take epsilon small enough, can be as regular as you want. However, higher derivatives get worse and worse with epsilon in that scheme. So every time you take a derivative, it's like epsilon minus 2, 3, 4. It's getting horrible. All right, and now I have 4 minutes. So in the last 4 minutes, I'll say something about this largeness. So this largeness looks horrible because, well, I didn't really talk about this even in the context of the solutions from uh, the last few lectures. But of course, right now, so we're on this v equals 0. And before we talked about constructing a solution here, right? Eventually, you want to do a naked singularity. You need to construct, go all the way out to future null infinity, you'll do all this stuff. Now, generally, in these kind of problems, if things are large, if things are size at 1 over epsilon, that looks pretty scary for controlling it on a long time scale. And there's not really, for these kinds of problems, so what the buzzword would be for a nonlinear hyperbolic equation, which is super critical with respect to its conserved quantities. That is to say, so whatever conserved quantities you have, just by scaling considerations, you can sort of tell are not going to be useful for saying the solution doesn't blow up. That is the case for the Einstein equations. You have some conserved quantities, but very simple heuristic considerations, that the fact that those quantities are controlled does not tell you if a singularity forms. For example, ADM mass is conserved, but you can have a black hole of arbitrarily small ADM mass. So ADM mass, that it's bounded, doesn't even tell you that you don't have a black hole or not. Okay, anyway, that's the basic idea. So for such problems, you need some other mechanism, and usually you need somewhere there has to be a small parameter. You can be extremely clever in how that shows up, but somehow there's a small parameter. And so this looks extremely bad. All right, but the key is to sort of think in an alternative way. I mentioned that this kind of like what I call the stationary point of view, it's nice in that it gives you the most concrete equations to look at, but there's also a sense in which it's kind of, it's the most rigid. It only looks exactly at the cone and it's not dynamic. All right, so there's another way to think about what's going on, which is the following. All right. So let's think a little more about chi-hat. Think more. All right, so we have this, let me write down somewhere. I have it one of these PDFs here. Okay, so here's the actual equation, say for chi-hat. Where am I? That. All right, equals. Well, I don't really need to write it all out. Yeah, all right, so you have this. Yes, and then I'm going to write plus sort of h. All right, so h is, let's say, stuff that you sort of, where there wasn't any, you had to do this weird, you had to consider maybe this weird kind of equation, but it kind of worked out, is all in h. All right, so let's think more about this chi-hat. So this is chi-hat's equation. All right, so now you say, okay, I've restricted this to v equals 0. I multiplied by this right power of v. I got this weird thing. Okay, fine. And it looks enormous. And so that just looks not great because, okay, if I want to argue like before, I'm going to have to make it compatible with some data here. And that's going to be really big. And how am I going to show this a naked thing? How am I going to show that the black hole doesn't form or something? All right. But what you do is you can say, all right, let's not restrict this to v equals 0 yet. Let's just do the following. So, let's say we have some good ideas about these things. Let's suppose that we do. Like I said, I just running, well, I'm already over time, but I said let's assume we've sort of understood everything else kind of to leading order except chi-hat. That's the final one. So, okay, the first, you can kind of replace these. Let's say we're trying to understand things happening pretty close to v equals 0, but not on it. So what you do is you kind of replace these with like their limits. And then you can still do that algebra, that conversion of the nabla 3 to a d by dv thing. Let's just not restrict it to v equals 0 yet. Let's just sort of leave it. And what you get is something kind of interesting. Well, what you get basically, I mean, you get something almost like that, but if you set sort of in some uh, logarithmic variable, so if you set, say, s equals log v, then what you end up with is, I mean, you just get the same equation, but you get with like a well, right at Lie, okay, Lie derivative of s, you get this, and then you have all the same things. So then you still have this. All right, so something like this. All right. So before, the way I got that equation was just that okay, so this in the v variable is like v times d by dv, right? And so when I said v equals 0, it sort of looks like it should go away. But let's not set v equals 0 because maybe we want to understand a little better what happens away here. Okay. And so you can look at this, and now, well, you can look at something much simpler. So let's look at like a scalar problem. So let's just look at something like you can have so u prime, yeah, like d u, well, we can even switch back to v if we want. We can look at du dv minus epsilon, this is like epsilon squared u, say, equals epsilon. And one solution that you can, well, I shouldn't use u because u is a null coordinate. Let's pretend it's like some, I don't know, let's say just psi. And well, there are different ways to look at this. I mean, one thing is that in this case, you can actually write down, quite explicitly something. So let's write, so you can look at, so what do I want to do? I say psi. Oh, I guess I really shouldn't just lecture into into infinity. All right, so let me just close up really fast. All right, all I'll say is, so this, of course, in principle, like you look at v equals 0 and that looks horrible. You have this 1 over epsilon blow up. All right, but what if you say, okay, I know it's going to be large, at least point-wise at this point, but maybe, I mean, if maybe I can be small in some other norm and it's fine. And well, you can look at this equation. What you can see is what I can do is I can I mean, basically I can check, I can use this and I can say, all right, I might blow up, but sort of it's only kind of as bad as like logarithmic in V. Or you note that in some sense, this is like a bad estimate because, well, I mean, it allows me to be, if it's weaker than I did the stationary theory, I froze this and then got all those things. This is weaker than that. But on the other hand, it tells me that, all right, it's true that I blow up, but I blow up extremely slowly. In particular, in those energy norms that we saw show up when we do like those bootstrap arguments, which are L2 in space, the L2 norm of this thing will be small. Right? And sort of, yeah, really just running out of time here, but the point is, okay, this of course depends on what initial data you put. So I tell him if you solve this and you set, for example, psi at v equals, so this is something that you're going to solve, say, you want to be true for v positive. So let's say you pick the solution such that v at delta is equal to 0. So you just pick that. Then of course, assuming everything is sort of assuming it ends up being that this thing is 0 on v equals 0, ultimately psi is going to be like 1 over epsilon. But you also can prove this, right? And then this turns out to be the key to running. Well, there's still lots of complicated things, but this is sort of the hidden smallness that you have to understand. This is what I was saying, that you need smallness to close these problems, but you can be sort of very clever in how that smallness arises. And so And one of the things, I mean, this in some sense dates back to Chris Sedulu's work on the formation of trapped surfaces, is that you don't need, you know, you can study interesting phenomena which require things to be large pointwise, as long as some other things are small and some LP norm. And again, just in the last 15 seconds, why is that? Well, we've sort of seen that we do these nonlinear problems. I mean, you prove some linear estimates, you do your energy estimates, then you have these nonlinear terms on the right-hand side, things that might mess you up. But those things are always going to be integrated, right? Space-time norms. So you control them. Those are ultimately, they're, if there's something as small in a space-time norm, then it could be that lots of those are ignorable, even if a few things are large in infinity. That's very, very briefly. Um, and anyway, that's sort of that ends up being kind of a key to controlling it. All right, so I think I should, otherwise I'll just go for another hour. So I think I should just stop there. All right, so thanks.